In this video, we finally get to the three-dimensional radial equation. We'll start by recasting the radial equation, and then we'll do the solution of the particle in a bubble. So if we get back to the radial equation with the potential included, we see that we can write it like this. d by dr of r squared d capital R, which is the solution for the radial equation, by d lowercase r, minus 2 mr squared over h bar squared, times the quantity v of r minus e, all times r, is equal to L plus 1 times r. This is a separation constant. The first separation constant where we separated the angular and the radial solutions. What we want to do now is change the variables to a new variable u of r, which is equal to lowercase r times the function, the solution r of r. And this allows us to simplify the equation. So if we replace r of r by u over lowercase r, we can see what happens. So the first term, dr by dr, is equal to dr by dr of u over r. Well, that gives you two terms. The first term is 1 over r du dr. And then the second term is minus u over r squared. So we can rewrite this by pulling out a 1 over r squared from both terms. We get r times du dr minus u all times 1 over r squared. That's the first term here in red. Then we take the term in blue and we apply this, the red term that we had already just decided, and we get d by dr of r du by dr minus u. And now the r squared has canceled out the r squared in the denominator from dr by dr. And so when we take this derivative, we get du by dr. Then we get r times d squared u by dr squared. So that's the derivative of this second term, minus du dr. And of course, these two terms cancel. We get r d squared u dr squared for this first term in blue. If we now put this in to the equation above, we have here r d squared u dr squared minus 2 mr squared over h bar squared times the quantity v of r minus e times u over r equals L plus 1 times u over r. We can now obtain a differential equation simply for u. And we multiply first by r. So we get r squared d squared u dr squared minus 2 mr squared over h bar squared times v of r minus e times u. We've canceled out the u, r in the denominator. And here we have this equal to L plus 1 times u. We now do a little bit of rearranging. We bring the energy over to this side, and we bring this term over here. And we get r squared d squared u dr squared minus the quantity 2 mr squared over h bar squared times v of r times u plus L plus 1 times u equals minus 2 mr squared over h bar squared eu. Finally, we multiply times the inverse of this constant, which is h bar squared over 2 mr squared with a minus sign. And we get, over on the left side, we get minus h bar squared over 2m. The r squared cancels out. D squared u dr squared. This looks very familiar. It's the first term of the three-dimensional radial Schrödinger equation. One-dimensional Schrödinger equation, sorry. And then you have v of r plus h bar squared over 2m LL plus 1 over R squared, all times U equals EU. And this is nothing more than a time-independent, one-dimensional Schrödinger equation for U with an effective potential V effective of R in green, which contains two terms. It has the the regular potential V of R, but then it has this additional term, H bar squared over 2m LL plus 1 over R squared, which is also a central potential. And of course, that's equal to an energy E. We can normalize this solution. If we normalize it, we go from 0 to infinity. U of R modulus squared integrated by dr is equal to 1. And that's the solution that we'll get. Our final solution then is capital R, which is U over R. So that's what we need to go back to at the end. So let's do a problem now. Let's imagine that we have an infinite spherical well. That is, we have the potential is equal to 0 for R is less than A, and it's infinity for R greater than A. So we have no V of R inside the bubble, and the wave function can't penetrate the bubble. So inside the well, the wave equation for U is just E times U is equal to minus H bar squared over 2m, d squared U dr squared, plus H bar squared over 2m times LL plus 1 over R squared times U. If we now divide by H bar squared over 2m and rearrange, we get d squared U dr squared is equal to LL plus 1 over R squared minus 2m E over H bar squared times U. So this is a very familiar kind of equation, except that we don't have just a constant times U, we have this term times U, and we have to deal with that. If we make the usual substitution of k is equal to the square root of 2me over h bar, then this becomes k squared. And so we have d squared u dr squared is equal to LL plus 1 over R squared minus k squared times U. So we need to solve each of these equations for each value, this equation for each value of L separately. We'll start with the L equals 0 value, and that'll be the simplest. So for L equals 0, we need to impose a boundary condition, the boundary condition being that at the edge of the bubble, that is U of A, is equal to 0. That means that the equation when L equals 0 boils down to having one term, d squared U dr squared by dr squared is equal to minus k squared U. We've solved this problem before. This has the usual solution of sine and cosine. So U of R is then A sine kr plus B cosine kr. But we now have to apply the boundary condition U of A equals 0. And for U of A equals 0, we also have to remember that the real solution we're after is R of lowercase r, which is U over R. And so the cosine of kr solution would be infinite at the origin. And so B has to be equal to 0. However, the sine kr solution is finite because at the origin, sine goes to 0, but 1 over r goes to 0. And so sine kr over r is finite. And so this solution survives, this solution goes away. We can now write that the solution is equal to A sine of kr, and we now apply the boundary condition. So U of A is equal to A sine of ka, which is equal to 0. And that, of course, quantizes ka. So ka is equal to n pi, where n is an integer, and the energies for the L equals 0 case are thus E sub n 0, n squared pi squared h bar squared over 2ma squared, just the infinite square well energies, exactly the infinite square of energies, with n is equal to 1, 2, 3, and so on. And L is equal to 0. We can normalize this. If we normalize it, we get the usual normalization. which is square root of 2 over a. And if we add the angular part of the wave function, remember this is just the radial part, we have to add back in the angular part, which is a spherical harmonic with L equals 0, and M is bounded by L, so M is equal to 0 as well. So Lm 0, 0. And that's equal to 1 over the square root of 4 pi. And so the complete solution then for n 0, 0, size of n 0, 0 is equal to 1 over the square root of 2 pi a, sine of n pi r over a divided by r. Because we now have to take u and divide it by r to get the radial function. So this is the solution for any value of n where L and M are equal to 0. We can graphically see what these look like. So this is psi of n 0, 0 is equal to 1 over the square root of 2 pi a, sine of n pi r over a divided by r. And if we plot psi 1, 0, 0, it just looks like smooth going to a at 0 at a and no nodes. N equals 1, pardon me, that's n equals 1. N equals 2 has a node and then goes to 0, as you might expect. N equals 3 has 2 nodes, goes to 0. And n equals 4 has 3 nodes, and so on. And so we can see how this behaves exactly in the way we would expect. That is, we have 0 nodes, 1 node, 2 nodes, 3 nodes, 4 nodes, and so on as you go to higher values of n. What about the solutions for L not equal to 0? Well, they involve Bessel functions, with the general solution being the following. U of r is equal to a coefficient a sub L times r times the Bessel function j sub L of kr, plus b sub L times r plus the Neumann function sub L, n sub L of kr, where Bessel function and Neumann functions are defined in the following way. These are the j sub L of x are so-called spherical Bessel function of order L. So j sub L of x is given by minus x to the nth power times 1 over x d by dx to the nth power sine of x divided by x. So this looks very familiar. Clearly, these are the sine type functions. And the Neumann functions of spherical Neumann functions of order L are the same thing with a minus sign in the front and a cosine instead of a sine. So as you might expect, for the problem we have, at the origin, these kinds of functions will tend to blow up. So, and that's because spherical Bessel functions are finite at the origin. Spherical Neumann functions are infinite at the origin because they behave just like what we had here was the cosine x over x. So we're going to set b sub L equal to 0, and so the solution is just a Bessel function times r. So capital R of r is just this coefficient a sub L times the spherical Bessel function of order L of kr. So we still have to apply the boundary conditions, and that is j sub L of Ka equals to 0. But unlike the L equals 0 case, this is a little bit more complicated. So let's take a look at what these spherical Bessel functions look like, actually. So j sub 0 of x is sine x over x. Well, when L equals 0, this term goes to 1. When L equals 0, you have no derivative, so it's just a sine of x over x. So if we plot this as a function of x, you can see what this Bessel function looks like. J sub 1 of x is equal to minus 1, well, there's a 1 here, so it's minus x to the first power. Then we have 1 over x to the first power times the derivative of sine x over x, which gives you cosine x over x minus sine x over x squared. And the minus sign comes because you're taking the derivative of 1 over x. Well, if I then do a little bit of carrying through here, carry this 1 over x over, I'm going to get into here, I'm going to get minus sign multiplying everything. So we now have sine x over x squared minus cosine x over x, and that looks like this. Now this function goes to 0 at the origin, and 0, and it oscillates. J2 has minus x to the second power times 1 over x times, and this is now the second derivative applied to this function here. So this function, I'm going to put this function j1, what we got for j1 after we took this derivative here. When we apply the first derivative, we have cosine x minus sine x, cosine x over x minus sine x over x squared. If we just put these, and then we have a 1 over x. So this gives me cosine x over x squared, cosine x over x squared minus sine x over x cubed. If I now want to put this over a common denominator, I have to multiply the cosine by x. So I get x cosine x minus sine x all over x cubed. And now I take the second derivative here. I apply the second derivative. When I apply the second derivative, and I take this out here, I get x squared times 1 over x. That gives me x. Then I take the derivative of this quantity here, and I get 3 terms out of this. The first term, and 2 are combined. So the first term is minus x sine x over x cubed. That's the derivative of cosine x. Then I have the derivative where I take the derivative of 1 over x cubed. So I have minus 3 times x cosine x minus sine x over x to the fourth. And when I take that and put it all together, I get that the derivative then is, the final quantity is 3 sine x minus 3x cosine x minus x squared sine x over x cubed. And that, again, starts at 0 and has oscillatory behavior. So these are the functions. And I show the fourth one as well. So the roots are not as simple locations, and you have to solve the roots numerically. So the solutions then for all L are as follows. They're J sub L of Ka equals 0, and K is equal to 1 over A beta sub NL, where beta sub NL are the roots. And the energies, E sub NL, are h bar squared over 2ma squared times beta sub NL squared. So what are the roots here? Well, for J sub 0, we already had the roots. The roots were very simple. They were pi and 2 pi and 3 pi as you go out. And the first root is at, it's very simple, right? Because that's just a sine squared. The J sub 1 is equal to 4.493 as the first root, then the second root 7.726, and so on. And you can see these are a little bit bigger than pi and 2 pi and 3 pi. And the J2s, the roots push out a little bit further, and the J3s, the roots push out even a little bit further. So the wave functions then we can write are psi of NLM of variables r, theta, and phi are equal to a sub NL times the Bessel function, the spherical Bessel function of the L of sub L of beta sub NL R over A times the spherical harmonic y sub Lm of theta and phi, and the betas are the ones given up here. So these states are 2L plus 1 fold degenerate states. Because the energy depends on beta, that means it doesn't depend on M. Right? It only depends on L and N. Right? So beta NL depends on the value of L and the value of N, of course, because it's up here. And so the energy is independent of M. And as we saw before from the spherical harmonics, the values of M which are valid are the values that go from minus L to plus L. And so that's 2L plus 1, different functions, spherical harmonic functions with the same value of L. And that means that these are all have the same energy and they're 2L plus 1 fold degenerate states.